Have you ever wondered what a perfectly thrown baseball and a satellite orbiting the Earth have in common? Well, believe it or not, there's some really elegant and surprisingly simple physics that ties them all together. And that's what we're diving into right now. All right, let's get right into it. And we're going to start with a scene that you've probably seen a million times in one way or another.
I mean, just think about a basketball swishing through a net or a paper airplane gliding across the room. How can we possibly predict that perfect curved path? Its motion isn't a straight line, so where do you even start?
So this kind of movement has a name. It's called curvilinear motion. And here's the real headache. At any single moment, the object's speed and its direction are changing. That sounds super complicated to track, doesn't it? Well, here's the cool part. It turns out there's a surprisingly elegant way to crack this code. But to really get a handle on the curve, we first need to look at the awesome tools physicists use to describe, well, any movement in space. And the star of our show today is something called a vector. It's a beautifully simple idea, really. It's just a measurement that has a size, how much, and also a direction. Which way? Just think of it like an arrow that's pointing the way, and its length tells you how strong it is. And this right here, this is the secret sauce. This is the big idea that makes all of this work. We take that one seemingly impossible curve and we break it down. We slice it up into simple, straight-line pieces using a coordinate system. The good old X, Y, and Z axis. Okay, so step one, we got to know where the object is in the first place. We do that by defining its position with something called a position vector. It's basically just an arrow pointing from where we start, our origin, all the way to its exact location in X, Y, and Z space. Next up, we need to know how that position is changing, and that, my friends, is velocity. It's also a vector, and it tells us two things, not just how fast the object is going, but the exact direction it's headed in at that very instant. And finally, to finish up our toolkit, we have acceleration. This third vector tells us how the velocity itself is changing. Is it speeding up, slowing down, making a turn? That's what acceleration is all about. So you've got position, velocity, acceleration. That's it. That's the whole toolkit. All right, so we've got this powerful toolkit. Now let's put it to work on the most common kind of curvy motion we see every single day, right here on Earth. We're talking about projectile motion. And this is basically any object that's been thrown or kicked or launched into the air, where the only major force acting on it is gravity. That's the key. And it means its acceleration is constant and it's always pointing straight down. Okay, now this slide is where the magic happens. This is the golden rule of projectile motion. We can treat the horizontal motion and the vertical motion as two totally separate, completely independent problems. Think about that. Horizontally, no acceleration at all. Its speed is constant. But vertically, it's got that constant downward acceleration from gravity. Splitting them up like this, that's what makes the whole thing solvable. This quote just says it all, doesn't it? To understand the curve, we look at the straight lines that create it. We aren't tackling some big, scary curve head-on. Nope. We're just looking at two simple, straight-line problems that, when you put them together, create that perfect arc. Okay, theory is one thing, but let's put this idea to the test. Let's get our hands dirty with a real-world example to see how this all plays out. All right, here's our scenario. We've got a sack, and it slides right off this ramp that's 6 meters high. When it leaves the ramp, it's moving perfectly sideways, horizontally, at 12 meters per second. The big question is, where is it going to land? How far away from the base of the ramp, that distance r, will it hit the floor? Okay, first things first, let's organize our thoughts and list out everything we know based on the problem and our golden rule. We know its starting horizontal speed is 12 meters per second. We also know that since it left horizontally, its starting vertical speed is 0. It's not going up or down at that first instant. We know the height is 6 meters, and, this is crucial, we know the accelerations, 0 in the horizontal direction and negative 9.81 meters per second squared in the vertical. That's just gravity. So here's our simple two-step game plan. First, we're going to use all that vertical info to figure out how long the sack is actually falling through the air. Once we have that time, we'll switch over and use the horizontal info to figure out how far it traveled in that amount of time. See? Two separate problems. So for step one, we're focusing only on the up and down motion. We can completely forget about the horizontal part for a minute. We pull out our classic physics equations and we realize, hey, we know the distance it has to fall, that's 6 meters, and we know the acceleration, that's gravity. The only piece of the puzzle we're missing is time, so we can solve for it.
And when you plug in the numbers and do the math, you find out that the sack is in the air for just a little over a second. 1.1 seconds to be exact. And that's it. That's our time of flight. All right, now for the fun part, the easy part. Step 2. We know the sack was moving sideways at a steady, constant 12 meters per second. And we now know it did that for exactly 1.1 seconds. This is where the beauty of our method really shines, because the horizontal math couldn't be simpler. It's just distance equals speed times time. So you multiplied 12 by 1.1, and the final answer is 13.2 meters. How cool is that? By breaking one complex curve into two really simple problems, we were able to predict its path perfectly. So, after all that math, what's the big picture here? What's the main idea you should walk away with? The big takeaway is this incredible, universal idea. Any really complex-looking problem, whether it's the arc of a basketball or even a satellite's orbit, can be understood by breaking it down into its simplest parts. And this isn't just about physics, right? This idea of breaking things down into independent pieces, that's a super powerful problem-solving tool for, well, almost anything. And that brings us to one last thought for you to chew on. This method works perfectly for flying objects, but where else could you use it? What big, complicated, maybe even overwhelming challenge in your own life could you start to solve by breaking it down into smaller, simpler, independent parts? Something to think about. Thanks for tuning in.